So you'll be able to see the things that we do in class afterwards. So I think that'll be helpful for you guys for studying for the exams. So we're going to start off with learning catalytics question, or sorry, a clicker question that comes from some of the material that we built on yesterday. And so this one says, I bring a positively charged rod close to a small piece of material. In one case, the material is made out of metal, and the other, the material is made out of some insulating material. What's the force that each piece feels? So in relation to the rod. Let's see where we are with our responses. So we've almost all agreed that it should be attractive, but we want to talk about why this is attractive. And so what's going to happen in the case of the metal in terms of the diagram that I have drawn here when I bring this positively charged rod close to it? So yeah.
All the negative charges move closer to the rod?
Right. So the negative charges are all going to be attracted to this, and so they're going to all move over here. So all the negative charges are over here now. And so that means what? This is kind of like the can example we saw yesterday, right? They're going to be attracted to each other. Okay, so that's the metal. So what's going to happen in the case of the insulator? Now with the insulator, let's put our electrons back where they were. Just kind of randomly around their atoms. So what's the difference between the insulator and the conductor? What do you think? What's the difference between those two?
Well, with the conductor, the metal, the electrons are freed, and then the insulator, they're not.
Right. So our electrons can't leave these atoms, but they can do something else. So what can the electrons do if they can't leave?
They can kind of like position themselves on like the side that's bored.
Right. So they're stuck to their atom, but they can kind of move around as long as they stay close to their atom. So they'll do something like this. And so because of this, you're going to have this, for any one of these particular atoms, the negative is closer to this than the positive is. And that makes this have a net attraction because the force is dependent on the distance, right? So this is just a tiny little bit further away than this is to this. And so that means that in the insulating case, it's also going to be attractive, okay? Good. So let's look at the next one. So I'm sure you guys have bought things off of Amazon before, because this is not the 19th century. So when you get things off of Amazon or when you get things mailed, a lot of times they have styrofoam packing peanuts. And so those packing peanuts are electrically neutral to start with. And what you find is they'll be in a bag or around some cellophane, which is also electrically neutral. So these things are going to rub together, and so what do you think is going to happen when these things rub together? You've seen it before, right? So what do you notice about it? Yeah, they stick together. So we want to know why they stick together in the context of the things that we've been talking about. So look at the way that I have these charges drawn on this slide. So for the neutral packing peanuts, I have like a bar that represents the positive charge, a bar that represents the negative charge. For the neutral plastic packaging, I also have a bar that represents the positive charge and a bar that represents the negative charge. So in order for these two things to be attracted to each other, what has to happen between these bars? Yeah.
Electron transfer.
Yeah, the electrons transfer. So what you see is that one becomes a net positive and one becomes a net negative, and then these things are stuck together. You see the same thing, there are videos online of cats jumping into boxes of styrofoam packing peanuts, and they're really unhappy when they find that there's this difference in charge. They have all these packing peanuts stuck to them. Okay. So this is more of an open-ended question. So you place an additional charge Q at a specific place on a neutral object by touching it. What happens to this charge if the object is an insulator or if it's a conductor? So again, go back to what we were talking about when it comes to the way that charge can move around on an insulator and a conductor, and that'll help you answer this one. So I'll give you guys about 5 minutes to talk about this one. Let's go ahead and talk about this one. So what do we come up with? What were some of the ideas that we had? How about somebody in the middle over here? What do you guys think? What do you think?
For the insulator, would there be like a local charge since the atoms would reposition and they would have to hold it in that specific part of the...
Yeah, so that's a good way to look at it. So what's going to happen is when you touch this, some of the charge is going to be transferred over, right? But in the case of the insulator, it's going to be local, right? Because the insulator doesn't allow the charge to move around. So I touch this to here, some of this charge is going to hop over here, but it's going to kind of just stay here, right? Because the charge isn't allowed to move. What about the case of the conductor? If I do the same thing with the conductor, what do you think is going to happen? How about over here, blue shirt? What do you think? What's ultimately the difference between the conductor and the insulator in terms of the way that charge behaves in it? Any ideas? How about over here? What do you think?
The electrons would be allowed to move more freely, so they're going to probably polarize inside of that.
Right. So the electrons are allowed to move freely. So when I touch this and they hop over here, they don't just stay there, right? Because the electrons don't like each other; they repel each other. And so what that's going to do is it's going to make these evenly distributed on the outside. They try to be as far away from each other as possible. Okay? Good. So let's look at another one. This is a little bit of a throwback to Tuesday's questions, but this kind of builds into some of the questions that we're going to have after this and the demo that I have. So this question says, I bring a negatively charged rod next to an electroscope without touching it. The electroscope is made out of metal. What happens? Okay, so let's go ahead and talk about this one. So this one's, it's really the same thing as the last question, right? Only the geometry is a little bit different. So again, we bring this negatively charged rod towards the top here, and that's going to cause the electrons to move as far away from the rod as possible, which means they're going to end up in these two legs here, which is going to make it repel. And so we can actually see this here. So I'm going to charge this rod here, this piece of fur, and if I bring it close to this, then these repel. Okay? So the next question, following along the same idea here, is what is going to happen if I touch the sphere when I have the rod close to it? And we want to talk about why, whatever our prediction is going to be, why that's the case. Okay? So let's go ahead and talk about this one. So bring the negatively charged rod here, and then I touch it after, we know what's going to happen when I do this, right? It's going to separate like that. But then we want to know what's going to happen if I touch this. So what were some of the ideas that we came up with? What do you guys think right here? What's going to happen when I touch this after I...
So if you touch it, you're going to remove that negative charge that you just transferred, and since it's not charged anymore, it would return to where it was originally.
Right. And so I'm not going to do this right now because this kind of leads into the next portion, the next question. But you're absolutely right. It's the negative charge is trying to move as far away from the negative charge that's up here in the rod as possible, and it's kind of far away when it's down here, but it can be even further away if it goes through my arm, right? Okay, good. So let's move on to the next one. So now we did this process. I charged this, I brought it close to here. I gotta charge it again. I charge it, I bring it close to here, and then I touch it. And then I take everything away, right? I move the rod away, I move my hand away. Then we want to see what's going to happen. Okay, so go ahead and talk about this. Okay, so let's go ahead and talk about this one. So what do we think is going to happen when what did I do here? I charge this up, I bring it close. We know that this is going to cause this to rotate. Then I touch it, right? So now that's the part. Now what's going to happen when I take my hand and the rod away? They're going to repel. Good. So why is it repelling? Why is it repelling? So what did I do when I touched it? Yeah.
When you touched it, you removed some of the negative charge because they're trying to distribute and space out from each other. So then when you take your hand away, since you removed some of those negative charges from the metals, they now, like, they still have some of the negative, but they have less than they had before, so they have overall a positive charge and positive repel.
All right, perfect. Did everybody hear what she said? Okay, let me repeat it again. It was very good. So what I did when I touched this was I took some of the negative charge away, right? Because we were at this point before, right? So let's kind of start from the beginning here. So we had everything's evenly distributed. And then when I bring this over here, this is going to push the electrons down here. So that's going to give this net negative charge. But then I touch it, and then the electrons want to leave because they can go further away than just being in the arms here. And so when they go away, there's going to be less electrons. But when I still have the rod here, you're still forcing whatever electrons are there to be down here, and that's going to balance the bottom. But then when I take everything away, I have a net positive charge, and that net positive charge is going to cause it to repel itself again. And that's exactly what we're seeing here. Okay? Good. So let's look at the next one. Okay, so I was looking for the Van de Graaff generator this morning. Unfortunately, I couldn't get it. I couldn't find where it was. But imagine this apparatus that we have here. So the way a Van de Graaff generator works is it has a metal sphere on the top and a belt that goes around via a motor. And that belt is going to rub up against a brush or something to collect charge, and then it deposits that charge on the top. Okay, so what we want to know is if I have this Van de Graaff generator and I put some pie plates stacked on top of each other, what's going to happen to them? Okay, so go ahead and talk about this. And I'll try to see if I can get the Van de Graaff generator on Tuesday. Okay. So what were some of the ideas that we came up with here? What were some of the ideas we came up with here? What do you guys think?
We're gonna start basically floating because they have the same charge.
Right. Right. So we're loading charge up onto the top dome here, and if we stack these metal plates on top, the charge always wants to move as far away from itself as possible, right? The negative charge tries to repel itself. So they're going to be moving into the top plate first, and as you're loading more and more charge, the charge up here is repelling some of the other charge, and that charge is going to end up on the plate below it. And as charge accumulates over time, it gets to be enough charge that it overcomes the force of gravity that's holding the plates down, and then they're going to repel each other. Okay. All right, so let's look at the next one. So, okay, this is just a slide that I'll talk through. So, we started doing calculations with Coulomb's law on Tuesday, and the way that I had outlined it in the video is actually a little bit different, you might have noticed, than the way that we talked about the calculations in class. And the reason for that is I made that video to be a little bit more general because I wanted to be able to use it with the calculus-based classes as well. And they do some more advanced things with vectors that we won't really worry about. So, like I said, there are two methods to apply Coulomb's law. The first is the magnitude of the force, and then saying that, well, once I calculate what the magnitude of the force is, then I can figure out what the direction of it is based on knowing whether I have two positive charges that are going to repel, two negative charges that are going to repel, positive, negative, they'll attract, and then putting the direction in by hand that way. This is the method that the book uses. It's easier in the sense because you don't have to break apart unit vector r hat, but it also requires that additional step at the end to say, okay, well, what are these charges in relation to each other? What direction should the force be? The second method was the method that I outlined in the video. This is the one that uses the unit vector r hat. It's the harder method. You need to understand the unit vector r hat, but it requires one less step, and ultimately it's the more general way to approach it. Both methods will give you the correct answer, and if you can understand both methods, then you're very well prepared. But when I'm not going to demo both to show the difference, but ultimately I'm going to be using the first method, the one that we used on Tuesday. Okay, so really quick recap from Coulomb's law. Again, this is a question that we did on Tuesday, but go ahead and calculate again what the units of K are, remembering that Coulomb's law says that the force between two charges as a magnitude is going to be equal to this constant K times Q1 times Q2 divided by R squared, and these are both magnitudes. So go ahead and do this dimensional analysis really quickly again. So let's go ahead and talk about this one. I think most of you guys got it. We did this one once already, but it's a good reminder of how to use dimensional analysis. I'll just do this really quickly. So we know that force has units of newtons, which is going to be a kilogram meter per second squared. The right-hand side, we don't know what K is a priori, but we do know that Q and Q both have units of coulombs, and that this distance is measured in meters. So what I can do is I can move all of this to the other side by multiplying both sides by meters squared and dividing by coulombs squared. So this ends up being meters cubed in the numerator times kilograms divided by seconds squared times coulombs squared. Okay, so let's move on to the next question. So this one's kind of open-ended, and you can bring in some of your colloquial knowledge of the term, but we want to talk about what's called the superposition principle. So what does superposition mean, and how do you think that's going to apply to these problems that we're trying to solve with Coulomb's law? So go ahead and take a minute or two to talk about that, and we'll discuss as a group afterwards. Okay, so let's talk about colloquially, what does superposition mean? What does it mean if I superimpose something on something else? Yeah. You add it, right? So if I have like an image, if I'm doing like some video editing or photo editing, and I want to superimpose something on it, it's kind of like a PowerPoint slide, right? You have a layer, you put a layer on top of another layer, right? So what do we think it might mean in the case of finding forces between charges if I superimpose something or superimpose the forces? Yeah?
You add the vector quantity?
Yeah, you add the vector quantity. So to give you an example, let's say that we have three charges like this. I can label this charge 1, charge 2, charge 3. Let's give them names, so we'll call this Q1, Q2, Q3. And if ultimately I'm interested in finding what the total force is on charge 3, what I do is I say, what is the force that 2 acts on 3? So that's like layer 1. What is the force that 1 acts on 3? That's layer 2. And when I calculate those two forces independently, I can just add them together. So the total force acting on 3 is going to be equal to the force that 1 acts on 3 plus the force that 2 acts on 3. Okay? So that's the superposition principle. Any questions about that? Okay. So we're going to have a couple of quick clicker questions to think about how we can use the superposition principle. And so this is the first one. So look at this diagram that I have here. We have 5 equal charges of plus Q placed on the square as illustrated. A 5th charge Q prime is placed at the center O. What is the direction of the resultant force on Q prime? And I have a note here, and I tend to say this a lot. When you're approaching a multiple choice question, a lot of times you shouldn't approach it like a multiple choice question. So it sounds like a little bit counterintuitive, but let me explain what I mean. Don't look at the answer choices and then say, well, I don't think it's this one, or I don't think it's that one. Look at the picture and think about what the picture is telling you, and then come to the answer before you choose what you think the answer should be. Okay? All right, so go ahead and take a couple minutes to look at this one. Okay, so let's go ahead and talk about this one. So when we're looking at this, what are some of the things that we're noticing? Yeah?
Charges B and C will cancel.
Right. So the force from the charge at B and the force from the charge at C are going to cancel. Why? Why are these going to cancel? What do you guys think? So force that this one imparts to this charge here is going to cancel this one. There's kind of 2 reasons for why, or there are 2 parts to why it is that those cancel. Yeah.
Same charge and same distance.
Right, it's the same charge and it's the same distance. So all of these charges are charges of just the plus lowercase q. And this distance is the same distance as this. And we know from Coulomb's law, which I erased already, but the force is going to be related to the charge and the distance. And so if those two things are the same, then the force is going to be the same. So these ones are going to cancel each other. Okay. What else do we see? What else do we see? Yeah.
Would the charge from between C and D to O and between B and D to O be the, like A to O is the sum of those two?
Did I label this wrong? Okay, can you say that one more time?
Yeah, so the one that's going up from the bottom.
Sure, this one.
And then the one that's going in from the right.
Uh-huh.
If you add those two together, would you get A to O?
Would I get the same force that I get from this one?
Yeah.
Maybe. But I think you're onto something though, because you know that this one's gonna cause a force that goes this way. This one's gonna cause a force that goes that way. But the question is, is that going to be the same? Is it gonna be stronger? Is it gonna be weaker than the one that this one acts this way? Because we kind of have a sense that these are the three vectors that we have, and I didn't draw them to scale. So I'm going to draw them roughly the same size on purpose, but they're not actually going to be the same size. So why would it be one way or the other? Why would this be stronger than this, or why would this be stronger than these two? What are our thoughts? Yeah.
So would the two on the side and the bottom be stronger because there's a shorter distance between them?
Right. So that's one part and one way to think about it. These ones are closer, right? So whatever force this one acts in this direction is going to be an amount that's actually, so it's going to have a larger force because it's closer. But there's also two of these charges, right? So the fact that I have two of these working together to create this versus this one at this point just acting down like this means that the force from these ones is going to be larger. Yeah. Do you have a question?
No,
oh, okay.
Say, like, isn't it just the superposition principle?
Exactly. That's exactly what this is. So if we want to find the total force, we're adding all of them up, and then the question really is, because we're not actually doing the calculation here, we just want to know, well, what direction is the force going to point? And it's kind of like a graphical, conceptual way to apply the superposition principle to do this. Okay, good. Okay, so we got another one that kind of follows the same vein here. So for this picture that I have here, what is the direction of the force that's acting on the charge plus lowercase q? And yeah, so these, this plus q and this minus q that are drawn here, these are the same distance away from the origin. Okay, it's not labeled, but assume that that's true. When you look at it, it looks like it is. Okay, but assume that they are the same distance from the origin. Okay, so let's go ahead and talk about this one. So the best thing to do on problems like this is to draw a diagram so you can represent the ideas that you're thinking about. And so I have this diagram of this situation where I have the positive charge that's on the y-axis here, negative charge on the y-axis here, the positive charge on the x-axis here. And we want to find what the direction of the force is acting on this. Now, we're really applying the superposition principle here, and so we take it step by step. Step one, we should look at, we could pick either one, but let's choose this one. What's the direction the force is going to point that acts from this one to this one? It's going to be down at this angle like this, right? How about the one that this one acts on this one? It's going to be down like this, right? So because of this, what we're seeing is that this one's going to attract it this way. This one's going to repel it this way. So what we want to do to find the total force is to add the force, the individual forces that are acting on this. And so we're going to see something kind of interesting when that happens, but it's only because of a very particular reason that this is going to happen. So when I add these vectors, it's like I take this vector, I can put it over here, and then the resultant vector looks like that, right? So that's just going to be a vector pointing straight down. But that's only because the distance here, this is the same distance, we can call it some distance d. These are also the same charge. Well, one's positive, one's negative, but they're both the same capital Q, right? So in order for this to add exactly 0.5 pointing down, they need to have the same magnitude of charge here, and they have to have the same distance. Okay? Does that make sense? All right, so let's move on to another one. Okay. So we have another slightly different arrangement here. We want to find what the electric force is acting on charge Q3. And this is actually, it's a calculation that we have to do here. And like I said, don't treat it kind of like a multiple choice question. Really think about how we can do this. Okay. So go ahead and take, this one's probably going to take a little longer. Take like maybe 5 to 10 minutes to do this. Okay, so let's go ahead and talk about this one. So I have this drawing here for our setup. And what we want to find is the force that is the total force that's acting on this charge plus Q on the right here. So what we're trying to find is F total acting on 3, okay? So based off of this, we know this is what we're trying to find. We want to use the superposition principle, right? So in this case, what does that mean? What does it mean that we're trying to use the superposition principle to find the total force on Q3? Yeah.
It's just the net sum of two or more forces acting on it.
Right. So we want to find the total force acting on this, which means we want to find the force that each one of these individually acts on it, and then we can add them together. So we want to find the force that charge 1 acts on charge 3, and the force that charge 2 acts on charge 3. Okay. So now we know this is kind of the direction that we want to go, and so what we need to do is individually calculate what the force is that 1 acts on 3 and what the force that 2 acts on 3 is, and then we can just add those together to find the total force. So let's first start with F13. F13 is going to be equal to K times the magnitude of the charge Q1, which is going to be 2Q, times the magnitude of the charge of 3, which is just going to be Q as well, divided by the distance between them squared. So the distance from 1 to 3 is going to be 2a. So we have 2a squared. Okay? So far so good. We can simplify this a little bit because when we square this 2, we're going to get a 4. The 4 is going to cancel with the 2 in the numerator, and so this is going to be a k q squared over 2a squared. Okay? Now let's look at the force that charge 2 acts on charge 3. The force that charge 2 acts on charge 3 is going to be, again, just K times this charge as a magnitude, which is just going to be Q, times this charge as a magnitude, which is another Q, so we get a Q squared, divided by the distance between them squared, and so this is going to be A squared, okay? So now we have the magnitude of the forces, but we need to take in consideration what these charges are trying to do to each other, right? So the charge Q1 is going to be trying to push this one away, right? They have the same charge, they're going to repel each other, which means that this force, F13, is going to point this way. The force that charge 2 acts on charge 3 is going to point this way because this is a negative charge, this is a positive charge. This attracts it, so it pulls it this way. So this says that this is F23. And so when we want to add these together to find the total force, we need to take that into consideration. And so what that means is that this total force, F total, 3 is going to be equal to, we're going to say that this is the positive direction. So we're going to say to the right is the positive x direction. That's a pretty standard convention. So this says that this is going to be equal to k q divided by q squared divided by 2a squared minus k q squared divided by a squared, and this all gets a unit vector I hat now because we have a vector sign here, we need a vector sign here. And so when we take this difference, what we really have, because we could factor out this kq squared over a squared, that's common to both of these terms. We really just have a half minus 1. A half minus 1 is just going to be negative a half. And so this is going to be minus kq squared divided by 2a squared in the I hat direction. Okay? Any questions about that? So this is a pretty standard kind of problem that I might ask on an exam, and there's a lot of variations of this that I could make. So for instance, I could tell you that these are different distances. I could say that this is A, this is B. I could change what these charges are, which one's positive or negative. I can make this 5Q, right? The calculation is going to be exactly the same. It's just a matter of evaluating for what I give you in the problem, okay?